Thank you, everybody, for joining today's webinar focused on an introduction to Flash Chromatography. Today, our speaker will be Josh Lovell. If you have any questions throughout the webinar, please use the chat function within the platform, and we will answer questions at the end. At this time, I will hand it over to Josh.
Thanks, Tori. So today I'm going to be discussing an introduction to Flash Chromatography, and we're going to discuss faster, greener, better separations. My name is Josh Lovell. I'm an application chemist here at Teledyne ISCO, and you guys can contact me at that email address. So today we're going to discuss what drives chromatographic separation, similarities and differences between Flash and HPLC. We're going to show a case example of the benefits of automated flash chromatography, how to get started with flash chromatography, including choosing a stationary and mobile phase, going from TLC method to a flash method, overall flash loading techniques and guidelines, ultimately how to optimize baseline resolution, and then finally we're going to talk about how our new Combo Flash NextGen product can take your chromatography to the next gen with faster, greener, better separations. So our first topic is, how does chromatography separate compounds? And so we start off with a system with two phases. We have our mobile phase, which in the case of Flash and HPLC is liquid, and a stationary phase, which is the column packing within the Flash column or HPLC column. Ultimately, what we're limited by is sample solubility. So we need the sample in solution at some point so it can absorb onto the stationary phase and interact. The separation here, so we have an image here of a reverse phase, functionalized stationary phase, interacting with the mobile phase and the compounds of interest here, these different anilines. So you can see that the molecules here are interacting with both the stationary phase, the functionalized stationary phase, and the solvent molecules, and that's what is driving the separation, is the interaction between both of these phases with the compound. This is the reverse phase example, and we're going to be discussing normal phase for the most part with the flash systems, but the same principles apply. So what's flash chromatography? It's a purification technique utilizing a stationary phase and a mobile phase. It's originally developed to replace open column chromatography, so we can have faster separations. Applied pressure to the column reservoir to speed up the mobile phase. And traditionally in the lab, you see silica gel used as a stationary phase, and you use normal phase, mobile phases. So why would you choose to use HPLC or Flash? And ultimately, the goal is to purify a mixture of compounds. We can quantify the separation of different compounds using the resolution equation. And so the actual formulas as part of this aren't very important to what we're going to be discussing today, but we can break the resolution equation down into three different factors that we can control. One is the efficiency of the column, two is the selectivity of the system, and three would be the retention of the compound in the system. And so we're going to discuss different ways that we can affect each of these variables and maximize or optimize the resolution for our separation. So first I want to discuss the basic equipment kind of set up for a flash system, and it's very similar to what you would see in an HPLC system. So we have our solvent reservoirs, followed by a gradient former and a pump where mixing takes place. And then we have our sample introduction valve. So for HPLC, you'd have an injection valve where you're putting your sample into. For the flash system, you may be doing a liquid injection onto the column, or you may be using an automated valve that allows solid load cartridge to be used. And then the compounds are going to undergo separation on the column. And then once the columns are separated out on the column, it's going to go through the detector. And if you're doing flash or prep HPLC, that detector is going to go ahead and trigger fraction collection. And if you're doing analytical HPLC, then you're going to go ahead and do integration and quantitation of your sample to evaluate the efficiency of the separation and the purity of your compounds. Now the differences between flash and HPLC. So flash chromatography is traditionally low pressure. It's less than 300 psi in most cases. HPLC is obviously a high pressure technique, and usually it's going to be greater than 1,000 psi. Flash chromatography has lower efficiency columns because of the pressure limitations. They have to have a larger particle size, so the back pressure doesn't increase as much, and they're traditionally less expensive and disposable or one-time use. For HPLC columns, because we're at higher pressure, we're not limited by the larger particle size. So we can use smaller particle size, which inherently is going to give us better resolution. This plays directly into the efficiency portion of the resolution equation. And ultimately, these are going to be more expensive, but they're reusable. So you can get, with a prep column that you take care of, you can get a lot of use out of that. Flash chromatography is really a focus on purification and speed. We want to try and get the compound as pure as possible, as fast as possible. And so we're always balancing those two objectives when we're choosing a flash chromatography method. While HPLC is traditionally a focus on analysis and quantitation, so we really need a pure separation where these compounds elute at different times so that we can analyze them and quantitate them. We're not interested in peaks overlapping. We want clear baseline resolution between peaks. Traditionally, with the increased resolution, this also offers a great late-stage purification for compounds to really bring your purity up into that 99% range. Flash chromatography is going to allow a higher flow in sample loading, so we go up to 300 mils a minute with our system and higher sample loading. And traditionally, HPLC is going to be a lower flow and it's going to be lower sample loading to minimize band broadening. Typically, with the flash chromatography system, we're usually working in the normal phase systems and using a silica-based column. HPLC reverse phase seems to dominate, using aqueous-based reverse phase systems and using modified silica. Traditionally, C18 is the predominant functionalization of the columns. So the advantage of HPLC over flash is you obviously gain higher resolving power. It's also offers information-rich detection options, enhanced quantitation and analysis. And there's really a broad range of stationary phase chemistries that are available for use to allow you to choose columns that offer better selectivity or retention for your compounds. The advantage of flash chromatography is that you gain speed, particularly when you're purifying grams or milligrams to grams of material. Typical purity of greater than 90% on a single pass. And the operation costs are significantly lower than HPLC. The acquisition costs of the systems are less. The higher sample loading means that you can do less runs, which saves you solvent costs. Obviously, the column costs are significantly different between the reusable prep columns or analytical columns versus a disposable one-time use flash column, and offers minimal method development time when you're trying to purify a crude sample. So the next section here is we're going to talk about some benefits that you can gain from using automated flash chromatography. We're going to go through a real-life example that shows some time, solvent, and cost savings. And so this is an old example, but it's a very good illustration of of how we can how the automated flash system saves you time and solvent and cost savings. So in this case, we're going to be separating these wine rub amides, and they have an RF difference of less than 0.1, so they're going to be pretty closely eluting. If you look at the TLC and 30% ethyl acetate heptane, we see compound A and compound B there, and you know they're almost touching on the TLC and 30% ethyl acetate heptane. So obviously our goal is to achieve 100% purity of both compounds, so we don't want mixed fractions. We want to minimize the amount of solvent, so we don't want a large gap between the elution of these compounds, and that's going to save us time and solvent and ultimately money. So this example is a separation on a 12-gram column. When we actually choose the TLC, so we actually see resolution between the two spots on the TLC at 30% ethyl acetate heptane. When we do that simulating an open column, we don't get complete purity between the two compounds. So there's 3 mixed fractions there, and there's 3 pure A fractions and 4 pure B fractions. And so those middle fractions would have to undergo purification again, or potentially is not usable. So as we lower the polarity of the system, we're decreasing the RF, and now we're seeing where we get 5 pure A fractions, 1 mixed fraction, and 5 pure B fractions. And so if we go 5% lower to 20% ethyl acetate and heptane, you can see where we get 11 pure A fractions, 11 pure B fractions. So these compounds are eluting more slowly, and you're getting actual separation. There's no mixed fractions now, and the RF difference at 20% heptane is about 0.07. So so that's a simulated open column. So that'd be simulating what you would be doing in the lab without an automated system, and that should show how many fractions you would get and how much solvent and time it would take. So if we applied a automated step gradient to this, which is difficult to do on the difficult to control in an open column, but easy to do in an automated system, we can obtain the improved separation in 15 fractions. Where we get 6 pure A fractions and 6 pure B, and then there's 3 empty tubes in the middle, basically. If we take that a step further and we do a focused linear gradient from 10% to 30% over 15 minutes, we're able to get a 16 fractions separated and 7 pure A, 7 pure B, and we're actually using less solvent over this time, and we've improved our separation. So there's less of a gap in between the elution of A and B, where once A is completely off, and B starts almost immediately with the linear gradient. Ultimately, if we summarize the things that are important to us, it's the solvent volume that we need to use, and that's ultimately going to cost you more money to use more solvent, and it's also going to cost you money to dispose of that solvent. If you compare the isocratic separation to the step elution and the optimized gradient, you save almost a third of your solvent use by using the optimized gradient, and we gain almost at least 8 minutes of time savings by using the optimized gradient in the automated system. So this kind of summarizes some real life savings that you could see by using an automated flash system versus doing the open column. I would say you'd also have additional time savings in that you're using pre-packed cartridges for your columns, and you're not having to pack your columns, so there's obviously savings there too. So the next topic we want to discuss is getting started with flash chromatography. So we're going to discuss different choices we have in selecting stationary and mobile phases. We're going to discuss how to transition from TLC, different loading techniques to get your samples onto the flash column, and then ultimately how to optimize baseline resolution and improve your separation abilities. So selecting stationary for Flash or HPLC. So as we discussed before, there's a wide variety of stationary phases available there. So I have this slide here that we've ordered basically the predominance of these different stationary phases in both Flash and HPLC. And you can see that silica predominates in Flash chromatography, followed by the C18, C18AQ, alumina, ion exchange, and then your functionalized diol, cyano, and amine columns are all available to you to use in the Flash chromatography systems. But silica really dominates the market. HPLC, on the other hand, you can see that functionalized C18 in reverse phase and C18AQ really dominate the HPLC stationary phases. Additionally, you'll see shorter functionalized C8, C4 columns, ion exchange columns, silica, diol, cyano, the functionalized amine columns also, and then you start to see the ability to use chiral columns to allow you to separate out enantiomers and chiral compounds, and so that's something that HPLC, that there's more medias for HPLC that may be useful for gaining resolution and separating chiral compounds. So as we discussed before, in the resolution equation, there's kind of three components we're interested in. One is the column efficiency and selectivity, and then retention. And so one, retention and selectivity are greatly affected by changes to the stationary phase. So if I go from, reverse phase from bare silica, normal phase to reverse phase, I see a switch in the selectivity and retention, a drastic switch. So those are things that we can change to maybe get better resolution between two compounds. The other factor is column efficiency, and ultimately that is going to be how well is that column packed, and that's going to be dictated by two different variables, particle size and the symmetry of the particles. Do you have spherical particles that you're trying to pack together? Are you packing irregularly shaped particles? So we're going to get better packing when it's spherical and the particle size is more uniform and the particle size is smaller. We offer two medias. Our Redisep, traditional Redisep is a larger irregularly shaped silica particle, and it's great for doing a crude purification, or if you have compounds that elute very far away from each other, it's great for getting separation that way. But if you need added resolving power, you can change your column stationary phase to the Redisep gold material, where you have a 20 to 40 micron particle size. It's a spherical shape, so it packs better, and ultimately it offers twice the resolution power. You can do higher loading amounts onto there, and you have higher optimal flow rates, so the columns can go faster, you can get done quicker. Next, we're going to talk about selecting your mobile phase system. So this is a really important slide that shows the differences in different solvents. So we can group solvents based upon whether or not they are hydrogen bonding acceptors or they're hydrogen bonding donors. As you see in the group 2, we have all the alcohols, and those are really good hydrogen bonding acceptors and have some donor ability too. But you're going to see a lot more hydrogen bonding ability. And then you have, you're also looking at the dipole moment of these different solvents. So we can kind of group solvents together based upon these different properties. Similar compounds are going to have similar effects on your compounds. For ethyl acetate and acetone are going to be pretty similar, but maybe that's a big enough, substantial enough change that it changes the resolution a little bit. So that's something you can change as a solvent system. maybe you need a more drastic change. So maybe instead of a group 6 solvent, now you're choosing a group 2 solvent. So that's a pretty big change. You're changing the hydrogen bonding ability of the solvent and changing the dipole. So these are good ways that you can jump from, if you need to choose a big solvent change, changing from a different group to another group or changing within a group. This is a good way that you can use that. So this should be found in our Flash Chromatography guidebook, which you guys can find online, and have instructions at the end of the webinar to access that. Another way we can classify solvents is based upon their solvent strength. In this case, we have a strong solvent methanol all the way down to hexane, and then everything in between. And so this example here shows a TLC using a 1-to-1 mixture of hexane ethyl acetate, and we have similar RF values for compound 1, but when we change to hexane dichloromethane, we're actually able to get better resolution between the two compounds. The RF difference is greater when we go through a 1-to-2 mixture of hexane and dichloromethane. So we decrease the solvent strength, the polar solvent strength, from ethyl acetate 0.58 to dichloromethane at 0.42, and able to get better separation between the two compounds. So we're going to talk about how we can turn our TLC data into a flash method. And so thin layer chromatography, is very essential to organic chemistry in the undergraduate labs. So it's something you learn early on. And ultimately what you're doing is you're spotting a sample onto the TLC plate using a glass capillary, and then you develop the plate using a solvent system inside a TLC chamber, as shown here. Once the solvent has eluted to the top of the plate, or near the top of the plate, we're going to mark how far the solvent moved, and then we're going to develop the plate and try and visualize our compounds. So once again, silica plates are the most commonly used, but we do offer silica plates for our other stationary phases that we offer in our flash as flash columns. Sorry. And so ultimately, the important data that we can get from a TLC is the RF factor or retention factor. And this is essentially the distance the compound traveled versus how far the solvent traveled. It's a simple ratio there. And so if we look at our target compound in this example, it traveled about 28 millimeters. The solvent front traveled 90 millimeters, and we have an RF of 0.31. You'll notice the impurities traveled much quicker. They eluted much faster up the plate, so they would have higher RF values. When we transition from TLC to flash, though, it's a little bit more intuitive to think about flash chromatography in terms of column volume. So TLC, as the solvent moves, the compound moves, and we establish the RF value. The easy way to think about this is that if you have a compound that elutes with the solvent front, that it would have an RF of 1, and that essentially that would be eluting at the same as 1 column volume of solvent. So it's traveling at basically the solvent front, and that would be one column volume to get it off the column. So TLC RF values are inversely proportional to the elution time of a component from a column as shown below. So CV equals 1 over the RF. So if we had a RF of 0.31 as we showed on the last slide, the CV is be 1 over 0.31, and we'd get a CV of about 3.2. So it would take about 3.2 column volumes to elute this compound off the column. And so the one thing to note is that our column volumes are listed on the column. If you're using our products, you can see the approximate volume of what that column is, so that you have an idea if it's 18 millimeter column volume column, then you would require 56 some milliliters of solvent to get that off in about 3 column volumes. So optimizing our TLC conditions, I should say optimizing our column conditions using our TLC data. So we're really interested in resolution and getting separation between our compounds. So if we have 2 closely eluting compounds, we want to be able to purify them, even if it takes a little bit longer. But to predict resolution, delta RF is not that great. Delta CV is going to be a better measurement of how well we can separate our compounds. For the flash systems, it's going to be a better predictor. One option the automated software or peak track software on the NextGen offers you is it offers a gradient optimizer feature. So essentially what you do is you can run 2 TLC plates with a single solvent system at 2 different concentrations. So for example, I would maybe choose 30% ethyl acetate and hexane and 50% ethyl acetate and hexane. And then I would look and I need the RF value for the target compound and the nearest impurity. So I need the RF values to be between 0.2 and 0.8 for these, for the system to work. And then I'm going to plug those values, RF values into peak track, and I can generate an optimized gradient for separation. So for example, in 50% B, this compound A travels 0.48, has an RF of 0.48, and compound B has an RF of 0.4. When I reduce the percentage of ethyl acetate, compound A now has an RF of 0.34 and B has an RF of 0.21. So now I can go ahead and plug those values in, and it's going to generate a gradient for me. So here's what the screen would look like in your method editor. You can see the gradient optimizer there in the upper right corner, and then that would bring up this dialog box where you would be entering your RF values for the 2 different solvent systems, and the instructions are there too. So the next section we're going to talk about how do we load our sample onto the flash column. And so the first question is really how much compound can we load onto the column? So we have established some criterion based upon the delta CVs of the separation. So you're looking at the nearest impurity in your target compound. And if you have a delta CV that's greater than 5, then if you're using a gold Redisep column, because of the added resolution of that, you could double the loading compared to using a regular Redisep column. So you could go up to loading up to 20% of your compound. So if you're using a 4-gram column, you could load 800 milligrams. If you're using a 330-gram column, you could load 66 grams of compound. If it's a little bit more difficult separation, so you've got a delta CV greater than 1, then we suggest 10% loading on either the Redisep or the Redisep Gold. And so with the Redisep Gold, you maintain the resolution you're gaining, and then you're also decreasing the loading amount for the Redisep column. So now you'd only be able to load 400 milligrams on a 4-gram column or 33 grams on a 330-gram column. And finally, if you have a really difficult separation where the compounds have a elution delta CV of less than 1, then we suggest doing a 1% loading, and that would be 40 milligrams on a 4-gram column or 3.3 grams on a 330-gram column. So this is where we really need to take advantage of the enhanced resolution we can get from the Redisep Gold column, and then we're also minimizing the loading so that we can get baseline separation between our compounds of interest. And there's 2 different ways that you can load compounds onto the column or onto the flash system. And one is you can do a liquid injection, and this is what you're, originally taught in organic chemistry when you're doing your open columns, is that you have a liquid sample and then you're loading it onto the column and kind of some of the same basic rules are going to apply. If the compound's a solid and it's not a liquid, then maybe you're dissolving the sample in a little bit of a weak solvent to add directly onto the column after you've done your equilibration. And like I said, the same rules apply as traditional column chromatography. You want to minimize the amount of solvent, and you want to use the weakest dissolution solvent you can get away with. So the weaker the solvent, the better, and the less of it you use, the better. Here's an example of using a strong solvent, and so visually you can see that on the column there on the left. And also you see it in the chromatogram where there's actual band broadening where the compound elutes at. And if you dissolve it in a weaker solvent, we actually get a tighter band visually on the column, as seen on the figure on the right. And then the band broadening actually in the chromatogram is inherently better there also. So you can actually see the differences in the two different loading techniques. Additionally here, if you have a solid compound, maybe solid sample loading would be a good method to introduce your sample to the Flash system. And the reason for that is it gives optimal chromatography. It's really good for hard to dissolve compounds that would require large amounts of strong solvent to do a liquid injection. And we can increase the amount of compound that we're loading on the column also. It minimizes the band broadening when you dry the solid load cartridge. If you don't dry the solid load cartridge, then it's similar to doing a liquid load injection. The solid load cartridge, so the first method you could use to do this is you dissolve your compound and then whatever solvent it dissolves in easily, and then you go ahead and start adding silica to it to absorb onto the silica, the compound onto the silica. And then you're going to evaporate the dissolution solvent from the silica mixture and then load the silica mixture onto an empty solid load cartridge cap. Method 2 uses similar, you dissolve the compound in a strong solvent and then you add the solution onto a pre-packed solid load cartridge, and then you dry the column cartridge using the cartridge air purge if it's equipped on the Combo Flash system. And so here's kind of two examples here, the purification using the pre-packed solid load cartridge after we've dried it. We get clear baseline resolution between the two compounds. If you look at the purity of the two fractions under using HPLC, you can see one peak, there's no overlap. When we do a solid load cartridge without drying it prior to the run, you can see that the bands have broadened significantly. We don't get that baseline separation. And when you look at the two fractions, you can see that it's actually still a mixture of two compounds, although the ratios of the two compounds are more weighted towards one than the other. And then finally, we're going to discuss optimizing baseline resolution. And so this is what different variables you can take advantage of to improve your separations. And so ultimately, like we discussed before, flash purification is a balancing act. We want pure compounds as fast as possible using the least amount of solvent, and that gives us time and cost savings. Ultimately, a separation is always going to be determined by how closely two compounds elute. So if you have two compounds that elute closely to each other, then that's going to be a difficult separation, and maybe you're better off choosing a different kind of column, different solvent system, making some changes that allow for increased resolution. If you have a large RF difference, we can take advantage of the increased baseline separation, and we can increase the loading amount of compound that we put onto the column. If this is the case, you're sacrificing resolution to maintain maintaining baseline separation by increasing the flow rate or shortening the gradient. If there's a small RF difference or delta CV, then you need to maximize the resolution. And so we're going to discuss the different ways that we can do that. So one way to do that is to optimize your method. So if you're using the Redisep gold columns, the RFID tag on the column is going to be recognized by the system. It's going to know that you've loaded a gold column, and you can choose to do a resolution or speed method. If you need the added resolution, we have lowered the flow rate of that, and we have a longer gradient in order to optimize the resolution of the separation. So other ways we can enhance it just from any general method or from the resolution method, so we can lengthen the gradient farther or further. You could focus your gradient over a range, so instead of maybe going from 0 to 100%, maybe you're going over a 20% range from 20 to 40% if it's early eluting. So trying to get a focus gradient of about 20% is really helpful, and we'll show some cases where that is shown. Another thing is you decrease the amount of sample you're loading, so increasing the ratio of silica or column size sample loaded, as we discussed in our loading guide, but you can always do that without necessarily following those guidelines. But you know, if you need more separation, then loading less is always going to help. Next, you could change columns. So, like I said, you could use a Redisep gold column instead of traditional Flash purification column. You could use a larger column, so you're increasing the ratio of silica to compound. That is affecting your loading ratio. You could stack two columns together, and that's a similar effect as going up a column, except you're gaining some resolution by going through a narrower column. Or you could try a different stationary phase. So maybe you want to change stationary phases completely, go to a reverse phase system or a functionalized, another functionalized silica option that might be better suited for your compounds. Another change you can make is changing your solvent. So, you know, traditionally hexane ethyl acetate or heptane ethyl acetate or your traditional kind of base solvent system that you start from, maybe going to DCM methanol or DCM and some other solvent may be a better choice, or changing to a toluene solvent, which you can do now with our NextGen system with the baseline correction, or choosing acetone, or making solvent changes in the solvent system can have great effects on the selectivity and retention of your compounds. So we're going to kind of show some examples using our new Flash NextGen 300 Plus system of how we made greener, faster, better separations. So combining the speed of the NextGen 300 Plus and the with our Redisep Gold, we offer our speed method. And so using a traditional Redisep column and using the same gold speed method that we use with our Redisep Gold column, you can kind of see the separation of the peaks using a traditional irregular particle silica gel on the left there. When we do this same method on using a Redisep Gold column, now we're able to get some baseline resolution. You see two distinct fractions. And so you're gaining, you can see the resolution you gain by switching to a Redisep Gold column with the better silica. Additionally, we're able to actually increase that baseline separation by using a focus gradient. So using that same Redisep Gold column, we focus the gradient from 25 to 35% there. And so the peak shape is a little bit different because we're not using as strong of a %B in our method, but we're able to get baseline resolution in the same amount of time. So we could actually load a little bit more compound maybe. And we have solvent savings from using this method, and time savings obviously too. To kind of summarize our savings here, so that was on a 40-gram column, 400 milligrams of compounds. And underneath where I've circled, you can see that the speed method there, we're able to do that in 5 minutes. Using the 300 plus, and that's 40% time savings based on our previous generation of product. of combo flash. And on the resolution method, which we'll discuss next, we have time savings of 30%. But across the different column sizes, you can see time savings of up to 50%, and up to 60% using the gold speed method over the previous combo flash generation. Additionally, so we've optimized the methods throughout also, so that these are all going at the same optimal linear velocity. So if I do a 4-gram column and I want to scale up to 120 grams, I can easily scale up, take that same gradient, scale up, and the compound should be eluting in a similar CV location as a smaller column, so it's easier to scale up that way. And we've also, with the enhanced capabilities of the 300 NextGen 300 or 300 plus systems, increased the flow rate to 300 milliliters per minute. And so this allows us to use optimized linear velocity up at the higher column sizes, which we'll discuss in a few slides here. Additionally, the solvent savings by using a shorter method, focus gradients, and increased flow rate. So for the 40-gram column, it was only 7%, but at the other column sizes, as we standardize the flow rates and the gradients and the gradient profiles, we can see solvent savings of up to 50% using the NextGen 300, 300 plus versus the previous combo flash methods. So this slide here is going to show you how we can increase resolution again by changing columns and focusing the gradient or lengthening the gradient. So this is using our default method or our gold resolution method, and so it's going to offer us a longer gradient and it's going to be a slower flow rate. That's a little bit more optimal for getting better resolution for the separation. So using a traditional Redisep column, which is going to be the irregular, so like larger silica particles, we're able to get baseline separation between the two compounds. When we use the gold resolution method, using a Redisep gold column, we see even better baseline resolution. And then when we use that same focus gradient that we used before over a longer period, you can see where we can get increased baseline resolution of almost a minute between these two compounds. So we can load more compound on there using a focus gradient, or we could even shorten the length of the gradient still. So today we've described the basic mechanisms for chromatographic separations. So what things we need to consider at the interaction of the molecule with the solvent in the stationary phase. We compare the similarity and differences between Flash and HPLC. We showed you guys a real-world example of cost and time savings using an automated Flash system. We discussed the importance of selecting the appropriate stationary phase or mobile phase. We presented some different sample loading techniques for Flash samples and revealed different ways to maximize resolution. And finally, we illustrated some other examples using the NextGen 300 plus series to show how automated Flash system can further save you time, solvent, and cost while maximizing your separation ability and the different ways that you can change the methods to fit your needs, to balance those needs. So I want to thank you guys for your time. So here's our combo flash chromatography product line. So you can see we have our NextGen line, which is the NextGen 300 plus, NextGen 300, and then we have our NextGen 100, which is a more bare bones system. We have our Easy Prep combo flash Easy Prep system, which is a hybrid flash prep HPLC system. We have our large scale torrent system for large scale purifications, and then we have our mass spec pure ion detector, which can be coupled with any of the other combo flash systems here that we offer. Online here you can find our guidelines and tactics for flash chromatography, the effective organic compound purification manual. So if you go to the website and click on Flash Guide, you guys can register for a copy of that or download a copy of that. We have some upcoming webinars on October 4th. Jack Silver, colleague in the lab, is going to be presenting on the purification of natural products. And then later on October 25th, he's going to be discussing purification considerations for peptides. And in November, at a date to be decided, I'll be discussing utilizing ELSD for the purification of poorly UV detected compounds. And then Jack will be presenting in December about the basics of prep HPLC. If you guys have any questions, you guys can contact me directly. My email address here. My phone number is also offered if you guys would like to contact me that way. But if you guys have any questions, feel free to contact me. I will try and get you good answers. And if not, I will find someone that can give us good answers. So I appreciate your guys' time today. Really appreciate the opportunity that you guys allowed me to present some Flash chromatography basics and how the NextGen can help you guys' Flash purification needs.